want to talk a bit about a few of the things we are looking at in my own division at Chalmers. So I picked two themes basically. Let's see if I can get this moving. So the first theme on land and biomass use, carbon cycle and climate, I might spend more time on that one than the second one, which is on what we call beneficial land use change, and connect that to biorefineries. So that's my plan for today. Much of the modeling we do, it is integrating the different sectors in society where you have biomass and bioenergy use, and then integrating with the Earth system, so the terrestrial part most closely, but also then linking not the least to climate. So we are very much looking at the way biomass and other energy systems are functioning within the carbon cycle. And there we tend to make a distinction between the fast domain and the slow domain, as you see here. And I should say also that this there is of course a natural exchange flux between these two domains, but as that is pretty small compared to the anthropogenic transfer of carbon from slow to fast domain. We usually focus only on the anthropogenic part. So I kind of shut one of the arrows down here just to emphasize that. What we also look at quite much, that is the biobased product that we produce, and then we also extend what we call the fast domain to include most of the biobased products. On the longer term, it might be that we'll recognize that part of this product pool is not inside the fast domain, but actually we will have products with a very that represent a very stable and long-term carbon storage. But most of these bio-based products are short-term, so they are in the fast domain. Still, they can represent a pool of carbon that then represents a storage of carbon outside the atmosphere. So in that sense, they're important also for climate change mitigation. So very much of what we do is really to investigate how land use strategies and biomass uses influence some of the arrows in the fast domain. So the exchange flux between the atmosphere and land, but also the flux of carbon between the terrestrial, between land, agriculture and forestry, and the bio-based product pool, and the bio-based product pool and the atmosphere. So these arrows are all affected by bio-based systems in different ways, which makes them more complicated than the fossil-based systems, as that really affects one flow, and that is the transfer of fossil carbon into the fast domain. So this is kind of a conceptual way of describing the concept of how we work. And I thought I could give you an illustration of how we model bio-based systems and how we try to explain climate impacts. And I will do that with a few slides showing somewhat schematic example of mitigation options. So we will look at deployment of fossil-based and bio-based systems and how they affect the global average temperature. And I look at this at fuels now, but I mean that could equally well be any other bio-based option really. It's just a matter of timing of carbon flows here. So you can look at it as illustrative of how we look at carbon balances, temperature impacts of different bio-based systems. And in this case here now, I will use some IPCC scenarios as a basis for the modeling. And you can see them here in the diagram. So these are a couple of the scenarios that were used in the sixth assessment report, and we also used the data from an extended data set that goes all the way to 2200. And here, these are, as you can see, quite ambitious scenarios here. I could pick more depressing scenarios where temperature continues upwards. It would be basically the same methodology, but here I want to look at a more positive future. So therefore we selected these ones. And the approach we take is that we will investigate how temperature development deviates from the development you see here if we use some extra carbon-based fuels compared to, I mean, that is in addition to the fuels that are already used in these scenarios. If we use extra fuels besides what's already used in the world, how will that affect the global average temperature development over time? So that is a way to assess the impacts of fuel use, you can say. And here are a couple of scenarios that I wanted to use to show how impacts can vary. So in both cases, we start using this extra amount of fuels in year 0. In one case, we expand this use up to during, I think it was 20 years, and then we keep the level of fuel use for the whole scenario period. So in this case, for 180 years, we use 1 exajoule more fuels than what was in the scenarios. And you can compare 1 exajoule with the total energy system is at the level of 500. So this is a marginal increase. And we have another case where we have more of a transition situation. We use more fuels for 80 years. And then this fuel use is phased out again and reaching 0 after 80 years. And then there is no more of that fuel use. So 2 different scenarios on additional fuel use. And the fuels are either coal or natural gas. So these are the 2 fossil fuels, or biomass-based fuels that are obtained from forests in this case. And these are forests that are already managed for timber production. So it is not going into natural forests and converting them into production systems, but this is really changing the way already managed forests are used to provide biomass for different purposes. And then how do we produce the biomass fuels? That has a quite significant impact on the climate, on the temperature. So therefore we include also a couple of different cases here to illustrate that. What we use as a feedstock for producing biofuels here, that is either we take forest residues, and these forest residues, if we did not use them as a feedstock here, they would be left in the forest and they would eventually decompose, and the carbon in these residues would then come up to the atmosphere, but at a later time. And then we would also use wood that otherwise would be harvested, but they would be used for producing other products than biofuels. And these other products would have different residence time in society, so they would store carbon outside the atmosphere for different time horizons. So this is the feedstock resource base that we use in this case now. So just to, before I show the results here, just to recapitulate what we did here, we want to investigate the temperature impacts of using some extra carbon-based fuels in this world that is moving towards a quite ambitious temperature target. And we investigate how we deviate from the temperature development that you see in the diagram. So the graphs I will show you soon, they represent a deviation from either the blue or the orange line that you see here. As you will see, when we use fossil fuels, this deviation will always be an increased warming, which is, I mean, intuitive for most people. I think if we use even more fossil fuels, the warming will be higher. But as you will see, when we use more bioenergy, it is a bit more complicated, and the impact on the global average temperature can actually go in quite different directions. So they can both increase and decrease. Okay. Yes, I should say that also. This is now a simplification that I run first, then I will illustrate how other aspects can affect the outcome. So in this case, the only thing that happens in the forest sector is that we go in there and extract some additional biomass that would otherwise either be left in the forest or would be used for producing other forest products. So there is no other change in forest management in response to this increased demand for biomass. I will later show how forest sector responses can change the picture compared to what you will see now first. So if we model this temperature impact, I should have prepared better to remember what I wanted to say. So this is also something I wanted to emphasize, that the biomass we use, I have included now 2 different cases. So one case is when the biomass, if it is not used as a feedstock, the time it would take until the carbon in the biomass is ending up in the atmosphere can be longer or shorter. And here I have taken 2 different cases. So either on average, the carbon in the biomass will be up in the atmosphere after 10 years, or on average after 30 years. So you can think that if it is up after 10 years, you typically use quickly decomposing residues in the forest, or you use biomass that would otherwise be used to produce rather short-lived products, like paper products that are used and after a while not recycled so much, but actually being incinerated, and then you send up the carbon in the atmosphere. So that could be the case when you have 10 years of residence time. If you have 30 years, you would have more biomass that either decompose slowly in the forest, or that is otherwise used to produce products with a longer residence time in society. So that could be that you have more biomass that otherwise would end up in building houses, for instance, wooden houses. So depending on what type of biomass you use for producing biofuels here, you will see that the temperature impact is quite different actually. Finally, I was allowed to show the results. So this is now the first case here, when we used biomass throughout the whole scenario period. And you can see the temperature impact of this extra use of fuels. And for fossil fuels, as I said, it's a steadily increasing warming, which is what everyone would expect, I think. The more fossil carbon ending up in the atmosphere, the higher the temperature. So this is also kind of the typical result of cumulative fossil CO2 emissions, that you have as kind of a linear relationship between emissions and warming. But as you can see, for the bio-based options, you do not have the same steady increase. Instead, you have a stabilization of the temperature impact, and it stabilizes at different levels of warming depending on what type of biomass we used as a feedstock for producing the biofuel. I'm sorry that actually both green lines are look the same here. One should be dashed, and the one that should be a dashed line here, the 10-year, that is the lower one. So if you use biomass that otherwise would have a quite short residence time in society, the level of warming is lower than if you use biomass that would otherwise have a longer residence time. If we, I should say that also, that of course you can look at two of the lines as you can compare them as an indication of the degree of reduced warming or the mitigation effect of using one fuel instead of the other. So if I go back again, take away that one. Fossil coal, it is this one. If you use fossil gas instead of fossil coal, you would have this warming level here. I'm sorry that the dashed lines are not showing up. I don't know why. So the difference in warming here, that represents a type of mitigation benefit, you can say. And in the same way, you can compare one of the fossil fuels with one of the biofuel options, and you can see how the temperature impact looks different, and therefore that is an indication of the mitigation benefit of using biomass here. So the other one, the other scenario, that was more of a transition scenario. You see here the energy use for roughly 80 years, and then it is no more additional fuels, and then you see the temperature effect of using these fuels. And here you can see also the difference between fossil systems and bio-based systems, in the sense that the development after the fuel use has ended is quite different. So for the fossil options, you can see that there is a slow decline in the temperature effect, which reflects the long residence time of the carbon in the atmosphere. While for the bio-based options, you have a more rapid decline, which simply is because of you have the additional effect on the carbon stored in ecosystems, that the storage that we're going down is increasing again when you stop using biomass for producing biofuels. And therefore you also have this quicker reduction in temperature impact. And after a while, you do not really see any temperature trace of the period with biomass use for energy. And just to be really emphasize that point, the difference between different biomass uses here, the temperature impact that I showed you, that is totally determined by the change in the amount of carbon stored in soil and vegetation and in bio-based products, because that is really what influences the atmospheric CO2 concentration. So therefore, if you use biomass that has a quite short residence time, it would be this one. You would then reduce the storage of carbon in products and in soils and vegetation. You would reduce that storage less, and therefore you also emit less carbon up to the atmosphere, which is represented by this dashed part of the box here. If you use biomass that degrades slower and have a longer residence time, you then also reduce the carbon stock more, and therefore you have more carbon in the atmosphere, and therefore more warming. So this is really you could say that the loss of carbon stock that has a similar climate effect as fossil CO2 emissions. It's a direct linear relationship between this loss and the temperature increase, the same as for fossil fuels. But one difference is that these carbon stocks can then increase again if we stop using biomass. So that's reversible, which is different to fossil, of course. And yeah, so why did I throw this one in? Maybe it was just to share my frustration. So in my mind, what I have showed you is really nothing sensational. It is basic science and very established understanding of how the carbon cycle works. Still, it has proven to be very difficult to explain. And as I write in the parentheses, I think that actually one reason for that can be that some people might not want to understand it because they see a benefit in describing biobased systems in relation to fossil systems, for instance, by referring to the fact that the CO2 emissions from exhaust pipes or chimneys are roughly the same or even higher for biomass compared to for fossil fuels. And therefore, it's a very effective way of communicating that biomass and bioenergy is not a good mitigation option. I do think also the other way around, that people that are in favor of biofuels do not always want to accept going deeper into all the complications and the complex interactions that we have to understand to really understand the climate impact of using biomass. And therefore they would prefer to say that actually we don't need to care about biogenic CO2 emissions. We can just assume it is neutral because it was sequestered from the atmosphere in photosynthesis, and later on we just send it back. So it doesn't really change the amount of carbon in the atmosphere. So we can think it's neutral and we do not need to care about it. And that's also, I think, a simplification that is dishonest and really not favoring a good development of strategies for mitigation if you want to use biomass for mitigation. Okay, now I wanted to go into one complication before I shift to the other topic here. As I said, we did not here look at any changes in the forest sector that could happen in response to an anticipated growing biomass market for different bio-based products. But in reality, forest owners respond to what they expect to see far into the future. They often have a quite long time horizon, but they do respond to expected market developments together with other regulations and laws and so on. So in reality, we need to, in addition to having understanding of these fundamental carbon balances that I talked about now, we also need to look at actors and how they respond to the anticipated future they see. And I will just illustrate that with a couple of slides here now. If we look, and now I take Sweden again because I'm lazy and I know these studies since I was involved myself, so they were easy to pick here. If we look historically in Sweden, we have had an increasing use of forest biomass for many purposes, including for bioenergy. And over a quite long period, this has increased in parallel with increasing amount of carbon being stored in forests and forest products. So we have had a period where we have increased carbon storage, and that has, of course, counteracted the global warming caused by our emissions. So this has been a very kind of important part of keeping down Sweden's climate impact, if you like. Then the question is, of course, if we now look into the future and we try to understand how these forest carbon stocks will develop if we do different things with the forest, then we might come to see that this steady increase in carbon storage will not continue and I mean, it will not continue forever, of course, that's well established, but maybe depending on how we use the forest, we can influence the development in the coming decades quite significantly. And just for the Swedish case, since our forests are so large, decisions about how to manage the forest and how to utilize part of the wood for different purposes really has a quite big impact on the total climate impact of our Swedish activities. And now this is, yeah, you should never apologize for what you show, so I will not do that, but I could have apologized. I will try to explain what I wanted to show here. First of all, this is only for illustration of the Swedish situation, and you shouldn't take this as a kind of something that can be generalized to be valid everywhere. But I just wanted to compare the forest sector with the transport sector, just to illustrate the importance of the forest sector in Sweden. So what you see here is the temperature impact of the Swedish road transport sector, it should be, until 2060. No, it is emissions until 2060, but you can see the impact all the way to 2200. And we have two scenarios here with different amounts of biofuel use. It is these two on the top here. So in one case, we have biofuel use stays at 2020 level, and that is the gray one here. It's called biofuels low. And then we have another case where we have a more ambitious use of biofuels. So it develops along the political goal that we had previously. This was actually given up as a political decision a while ago. But at a point in time earlier, we had a more ambitious political goal, and then biofuel share reached 59% of road transport fuel use by 2030, and after that it stays at this level. So either no increase at all in biofuel use, or a quite ambitious increase. So the ambitious increase, that is the warming that you see here, the orange one. So these two, then you can compare with the dashed line here. And what I did here was that I combined the more ambitious biofuel scenario, so the orange one here, with a scenario for a change in the way we manage our forest. And in this case, I assumed that we fertilized forest stands roughly 10 years after felling, more extensively than we have done historically. So the annual fertilizing was covering every year an area that is roughly 1% of the forest available for wood harvest. And that is done to increase the forest growth and to support an increased wood extraction for producing more products. And one of the products could be biofuels. As we have increased growth here due to the fertilization, we also have a stronger sink. And this is what you see here. So if you combine the warming associated with the biofuel scenario with a kind of a parallel change in forest management, possibly among others to support the need to meet the need for biomass for producing biofuels, you will see that the total effect, the total warming effect, looks like this. So you actually end up with a slight cooling as a consequence of this. And it's this cooling, as you can see here, it really is the outcome of decisions about forest management. So that is a very strong determinant of development in Sweden. Now I'm sneaking past a few slides here because I can see the time is moving quite quickly. So I was just elaborating on this a bit here, but I will skip that. because I would like to talk about what we call beneficial land use change just for a short while. So I hope, I will share this presentation later. I hope you can send it around, and then you might be interested in the publications here, and they should be open access, all of them, I think. But they are the ones that providing the data that I will show you. So beneficial land use change, that is I don't know who invented it, but I believe it was a kind of a reaction on a very negative debate about land use change connected to the ILUC debate that we had some years ago, that brought a common view that any change in land use will be negative. So you should never develop systems that cause land use change, basically. And then beneficial land use change was kind of a counter argument that actually a lot of what we see in agriculture today is quite negative. So what we really need is land use change to correct the impacts we already see. And then we need to figure out what are the beneficial land use changes that need to happen. And that is also what we have investigated in some studies, how you could be more strategic about trying to achieve land use change with the purpose of addressing some environmental impacts you see of the current land use. And in these studies, we have looked at Europe, and we have focused on integration of perennials in areas that are dominated by annual crops. And that is illustrated here. Here you can see, if you go to the red, you have very high dominance of annual crops. And if you move towards the green, you have no dominance of annual crops. And then the yellow is in between. And what we looked at was how we could change the dominance of annual crops through changes in crop rotations. And basically, just to illustrate, it was done differently in different places, but you have simply less years of annual crops and you have more years of perennials. In this case, we were modeling grass clover mixtures being introduced in a couple of the rotations. And then we looked at how that introduction of perennials could reduce some of the impacts we see. And as one example, connecting to climates, we looked at soil carbon loss in Europe and how an overlaying maps of soil carbon loss with maps of the dominance of annual crops. And based on that, we could investigate a mitigation effectiveness related to the introduction of perennials. So where you have a high dominance of annual crops and you also have a high soil carbon loss, the mitigation effectiveness is higher. And then more soil carbon, you have enhanced soil fertility, but you also had other beneficial effects of this introduction of perennials. So you have better weed and pest management, you can use less pesticides, yields are more stable and higher, you have lower drought impacts, and also you have an enhanced biodiversity. So there were many additional benefits recognized from this, and that is also quite well established in many studies. We also looked at other environmental impacts associated with current agriculture. So besides soil carbon loss, we looked at nitrogen emissions to water, flooding, and then erosion, also connected to water, but also wind. And then introducing where we recognize the highest mitigation effectiveness of introducing perennials in relation to any of these impacts. We then modeled such an introduction, and then we quantified how much biomass one could produce based on addressing environmental problems through introducing perennials. And this is a similar approach that we have had in studies where Aarhus University is also involved with Chalmers, where we also specifically look at biorefineries using these perennials and the grass and clover that we cultivate. And then in addition to the benefits that I was describing now, we also have the benefits from producing biorefinery products. So we have biomethane, substituting fossil gas. We have not the least important, maybe the most important in this product, we produce high quality protein feed that can substitute soy-based feed. And we also have less need for synthetic fertilizers. So if we take our modeling, so this is so the numbers I provide you now, this is just to illustrate the kind of the scale of things, and it basically just make the case that this is worth looking at closer to really understand the potential for implementing these systems in different places in Europe. But just to give you the size of things, if we would have this large scale deployment that we modeled for Europe, the biomethane production would basically be at the same level as the target set for EU in the Repower EU 2030. So it's a significant amount. If we look at the benefit of substituting fossil gas with the biomethane, but also considering the soil carbon storage increase, you would have a net annual greenhouse gas savings of corresponding to roughly 50% of EU's agricultural emissions. So again, it's a quite significant mitigation opportunity for the agriculture sector here. And then we did not consider here in that 50% that we have a less need for synthetic fertilizers, and possibly the most important, that we reduce deforestation pressure in soy exporting countries, and that is not only a climate benefit but also a big benefit for biodiversity. So that's maybe, I would say, yeah, maybe the strongest driver recognized right now, at least, that we can reduce the import dependency of soy. The issue of ILUC here now and the displacement effect, of course, we introduce perennials, so we displace annual crops, and there will be a net displacement effect of this. But when we consider the beneficial effects of changing crop rotations on the yield levels and yield stability, and also that we consider the reduced need for importing soy, at least in the more optimistic cases, we model several different scenarios, but in the more optimistic cases, I would say that the net effect on the land requirement is possibly actually a land saving. So we would not have a displacement effect with deforestation somewhere in the world to provide agriculture products that need to produce somewhere. So that's a very positive outcome. And that was my last slide.